Hello everyone, my name is Xintao. I am a PhD candidate from Royal Institute of Technology in Sweden. The topic of this presentation is defining and generating axial lines from straight center lines for better understanding of urban morphologies. This presentation is divided into 5 parts. The first part introduces the background and some important concepts in this study. The second part presents the methodology. The third part shows the study area and the data, and the fourth part is experiments and analysis. The last part is conclusion. First, let's take a look at the concept of geographic space. Geographic space in the urban environment is a large-scale and continuous space where people can freely move around. It is beyond the perception from one single viewpoint. The space that viewed from one single point is called small space. Obviously, geographic space consists of numerous of such small spaces. On the left is the most used example of Gessentown in the study of space syntax. We can see that the light yellow part is the buildings and the light blue part is the geographic space. On the right are 2 kinds of representations of small spaces: convex map and axial lines. The space inside the closed planes is a large, continuous geographic space. A kind of representation of small spaces can be clearly seen in the form of collectivity graph. Now the question is, how can we objectively divide and evaluate different parts in geographic space? Space syntax is the answer. Originally, the theory of space syntax was developed by Behinia and his colleagues in the late 1970s. It is a set of theories and tools used for spatial morphological analysis with particular applications in urban science. Space syntax decomposes a geographic space into small spaces and then converts the small spaces into collectivity graph based on the spatial intersection relationships. According to the graph theory, we can quantitatively assess each individual part. Space syntax is a network thinking of space. Axial line is a fundamental tool. Axial lines are the longest visibility lines for representing individual linear spaces in urban environments. The least number of axial lines that cover the free space of an urban environment or the space between buildings constitute what is often called an axial map. Now let's take Gessentown as the example again. The solid red lines are the axial lines of Gessentown. Each axial line represents an individual space. They connect each other and cover the entire geographic space in Gessentown. All the axial lines together are called axial map. The important feature is that the number of axial lines is the least, which means each axial line is the longest one in the represented space. Then we can convert the axial map into graph, where axial line is the node and the collectivity is the link. Based on the converted graph, we can use metrics of space syntax to quantify the represented individual spaces based on graph theory. The metrics are connect, control, mean depth, global integration, local integration, total depth, and local depth. For example, the colored axial map is rendered by the value of local integration. It shows the difference between axial lines in terms of local integration. Now the question is, how was axial lines generated? Are there any problems in current solutions? The first reason is manual generation of axial lines is a tedious process. It is time-consuming, subjective, or even arbitrary. Second is that alt solutions such as depth maps and axial gene currently do not work for large-scale cities. We believe that the dilemma is because of the ambiguity of the definition of axial line. Therefore, the objective is to give the new definition of axial line and the old generation of new axial line in large-scale city for a better understanding of urban morphologies. The new definition is axial lines are the least number of straight lines that are mutually intersected along individual natural streets, because the free space in larger cities is not always walkable. Instead, only streets or sidewalks are truly walkable. Based on this new definition, an automatic generation of new axial lines is developed. The new definition of axial line is based on the concept of natural streets. To understand a natural street, we give example of road segments and deflection angle. On the left, we can see there are 16 road segments. They are connected with each other. The small hollow circles are the junctions where two or more segments are connected. On the right is an example of deflection angles as junction of three segments, 1, 2, and 5. The deflection angle is easy to calculate by means of computational geometry. Natural street is defined as individual adjacent road segments which have the smallest deflection angles. It forms a good continuity based on the principle of Gestalt psychology. We can see that there are 7 natural streets in different colors, which are formed by the every best fit joint principle. Based on natural street, we develop an automatic solution to generate axial lines. This process is very similar to the Douglas simplification algorithm. We connect the first and the last points of natural street to form a straight line, which we call baseline. Then we find the point that is furthest from the baseline on natural street. In this way, we get 3 parameters. First is the distance x, second is the baseline length d, third is the ratio of x divided by d. Repeat this process. The original natural straight line is recursively divided. When distance x and ratio satisfy the given thresholds, this process stops. This figure shows the first step of the algorithm to the natural street in red color. Repeat this process, we get more divided lines. The subscripts L and R mean left and right. This is the third step. When both x and ratio satisfy the given thresholds, the process stops, and we get 5 axial lines for the red natural street. Applying this algorithm to all the 7 natural streets, totally we get 12 axial lines. From above steps, we can see that it is a straightforward 3-step method to generate new axial lines. First is to generate natural street from road segments. Second is to determine the thresholds of x and ratio. Third is to apply the algorithm to natural streets to generate new axial lines. The process of calculating thresholds is we repeat the algorithm to all natural streets until x is equal to 0. Then we take the mean values of all x and ratio as the thresholds, because both of them follow the heavy-tailed distribution. It turns out that this method performs well in lab experiments. How can we get the study area data? Thanks to the success of OpenStreetMap, road networks of most of the countries in the world are now freely available. We download the original data from OpenStreetMap and retrieve the highway as road networks. We select 6 cities as our study area. They are Copenhagen, London, Paris, Manhattan, San Francisco, and Toronto. The 6 cities reflect typical street patterns in the literature, representing different morphological structures. The 3 European cities look irregular and self-evolved, while the 3 North American cities are grid-like and plain. It should be noted that we need to convert the highway into road segments first. This process is done by ArcGIS tools. The figure shows the process of this topological operation. Based on the processed data, we conduct the experiment on 6 cities. First, we get the natural streets and visualize them according to their local integration. We will see that the patterns are different from what newly defined axial lines have. Before generating the axial lines, we need to determine thresholds of two parameters, x and ratio. Because both x and ratio follow a striking log-normal distribution, we take the mean values of x and ratio as the thresholds according to the head-tail division rule. Based on the natural streets and determined thresholds, we apply the automatic algorithm to 6 cities to generate the new axial lines. We can see that the time efficiency is quite good. That means it works well in large cities. This is the visualization of new axial lines according to their local integration. We can see that the pattern is clearer than the one of natural streets, which means a stronger hierarchical structure can be retrieved for a better understanding of urban morphologies. To provide a further proof, we first give the visual comparison of London old axial map and the new axial map. The 4 patches indicate the 4 sites where observed pedestrian flow data are available for our comparison study. This is the local view of new axial lines and old axial lines of Clerkenwell site, which is one of the 4 patches. The red points are the pinpointed gates. This is the right-screwed log-normal distribution for both old axial lines and new axial lines of London. Furthermore, we get the R-square values between local integration and pedestrian flow for new axial lines, old axial lines, and natural streets. According to the results, the new axial lines capture well the pedestrian flow, at least as good as the old axial lines or natural streets. However, given the fact that the generation of the new axial lines can be done automatically, the newly defined axial lines are a better representation than the old or conventional ones. The new definition is less ambiguous compared with the conventional one. Based on the new definition, we develop an automatic solution to generate the axial lines for 6 cities. We have illustrated through experiments and comparison studies that the new axial lines can capture the underlying urban morphologies just as good as the conventional axial lines and the natural streets. Because it is an odd solution, it is a better representation for large-scale cities. Thank you. And any questions?